All right, so my project is entitled Assessing Machine Learning Replication of Long-Term Dynamical Behavior, also known as climate. So one use for machine learning algorithms is to predict a time series. So modeling a system of differential equations, which you can't solve for exactly, and predicting a time series which follows those equations. There are a couple different ways that we can quantify the performance of a machine learning algorithm predicting a time series. One way is looking at short-term predictions. So here on this graph on the left, you'll see that the machine learning predictions in blue agree very well with the orange truth or test data to a certain point. That's short-term predictions. We can also look at long-term climate replication. So that refers to how well the machine learning predictions capture the general look and feel of the system that we're trying to model. So on the left, you'll see that even after the predictions lose the exact trajectory, they still look like the system that we're modeling. They still look like the actual signal. Versus in this graph on the right, we'll see that the predictions agree very well to a certain point, but then once they lose the exact trajectory, they're going off and doing something that looks nothing like the system that we're trying to model. So the goal of this research is to be able to distinguish between these two cases without having to look at the graphs. So we want a simple objective metric that can quantify what's the difference between these two situations. And then we want to ultimately use that metric to guide research on how to make machine learning predictions replicate the climate better. So we're using the Lorenz equations, a famous example of a chaotic system as a test case for this research. This is a typical Lorenz trajectory. We're using the reservoir computer as our machine learning scheme for this work. So a reservoir computer is a type of neural network where we only train the connections going from the internal neurons or the reservoir going to the output. So these connections in yellow is the only thing we train. All the other connections are left random and fixed. So when we're training a reservoir computer, we're putting in inputs, which is a three-dimensional system state vector, and then the outputs are the system state at the next time step. So that's in training. When we're using the reservoir computer to make predictions about the time series, we're feeding that output back in as an input, and then that's going through the reservoir and giving us the next system state. So once again, the goal of this research is to be able to distinguish between good climate replication for reservoir computers and bad climate replication for reservoir computers. So these are a few examples of how reservoir computers can lose the climate in predictions. So this is a plot we've seen a couple times. Here we're agreeing well initially, but then we're going off in small amplitude oscillation. In this next case, we have predictions going down to a fixed point and staying there. And then in this last case, this is a little bit more subtle. Here it's clearly doing something chaotic, and it looks kind of like the Lorenz system. But you'll notice it has these weird features that don't quite look like Lorenz. Things look a little bit wonky. So we'd love to find a metric that can capture all these cases and distinguish them from a case where the predictions are capturing the climate well. So we settled on a composite error metric. So this uses a couple things. The first is a single step error metric. And the way this works is for each point in the prediction set that the reservoir has predicted, we go to the previous prediction, and then we use the Lorenz equations, and we say, what would the Lorenz equations have given for the next time step of the system? And then we compare that value that the Lorenz equations would give versus that value in the prediction set. So that gives us a step of how well the reservoir computer is predicting each individual time step versus the Lorenz equations. And then the other metric that we're using in this composite metric is the variance of the X dimension data. So in these plots, you'll notice that these here on the left, the predictions have a very low variance when they just go to some point and then either do a small amplitude oscillation or just stay at a single point. So both of these cases have very low variance, which distinguishes them from cases when we're getting good climate replication. Now this case is a bit trickier because it has high variance like the Lorenz signal, but it has these more subtle features where it loses the climate. So these cases are caught easily by variance, and then that more sophisticated single-step error metric is good at catching cases like this. So I made this plot here on the right. On the X, we have the variance of the X dimension predictions. And then on the Y, we have this single-step error metric. So each of these points represents a prediction series that I looked at. And then I visually just determined, is this a good climate replication case or a bad climate replication case? And I did that without looking at either of these metrics. But then when you plot those metrics using the variance and the single-step error, we get this graph that nicely separates the climate replicating predictions versus the non-climate replicating predictions. So from this point, rather than having to look at each individual plot of predictions and say, does this look like it's replicating the climate or not, we can say, we can basically draw a box around these good climate replication cases and say anything with variance and the single-step error metric that falls within this box, we're going to classify as having good climate replication. So what's an application of this new metric? So we ultimately want to use this metric to guide research on how to improve climate replication for reservoir computers, but for machine learning more generally. So with some reservoirs, if you don't give it any noise or just random variation in the training data, it'll do pretty poorly. But as you add noise, you can get a greater fraction of your reservoirs to give good climate replication. So in this graph, we have noise scaling on the X. We have the fraction of stable reservoirs using this new metric that we've developed on the Y. And you'll see as you increase the noise, you get this optimal value where you get significantly more reservoirs giving good climate replication. So each one of these points represents 300 reservoirs, and on the Y is just a fraction of them, of those 300 that gave stable predictions that fell within that box. So that's an application of how this stability metric or climate replicating metric makes it easier to study stability or climate replication. Thank you so much to my awesome research group and to Dr. Serrano.